Thank you for inviting me. Thanks, Professor Zhang, inviting me here. It's a great honor to have this opportunity to introduce our recent work on the quantum damping of the cosmological shield. This is a prediction from the quantum cosmology in the modified model, and later I will introduce the model. And this work, this talk is based on these two works, one of which is just accepted by PRL. And collaborators are from Brazil, Dr. Graf, Professor Ramos, and Dr. Vincent, and from America, Professor Andrew Wong. Okay, so my talk is divided into 7 parts. First, I will briefly introduce the motivation about the anisotropy problem, and then I will go over the basic knowledge about the quantum gravity and the quantum cosmology. I know most of you may have been familiar with this part, so I will quickly go over this part. And if you have any comments, you can, we can discuss later. And I will mainly focus on the modified model about the so-called MLQC1. It is alternative quantization prescription that deal with the Lorentz part and the Euclid part of the Hamiltonian different way. And then I will focus on the quantum damping mechanism. Later we will see it is just the different treatment of the Lorentz part and the Euclid part which introduce the asymmetry bounds of the loop quantum cosmology. And then this make the quantum damping of the cosmological shield. And finally, I will show the numerical results and the conclusions. Okay, so first about the motivation about the anisotropy problem. As we know, our universe is isotropic, and there is no macroscopic anisotropy. So this is a problem. Why our universe is isotropic? If initially the space-time is anisotropic, then the shield, which describes the anisotropy, will grow as 1 over a to the 6 during the contraction phase. The contracting phase is before the bounce. So during this phase, the shield grows like that. It will dominate over the matter and the radiation, and this part will behave like a stiff fluid. And since the matter grows with the 1 over a to the 3rd, and the radiation grows like 1 over a to the 4th. So shear will grow quickly than these two parts and will dominate in the pre-bounce dynamics and leave large post-bounce imprints. So this is a big problem in the cosmology. If there is anisotropy before the bounce, then it will remain still after the bounce and it will dominate during the bounce. So how to solve this problem? There are several methods. For example, some people will introduce the so-called erotic phase. It requires a fine-tuning of the potential of the scalar field. And in this case, it may solve the anisotropy, but it depends on the fine-tuning of the potential. And for the standard QC, it can solve the singularity, it has bounce. But in this model, we will later show that the shield does not decay significantly after the bounce. It will remain still right after the bounce. And another method is about the cosmological constant. If we put an cosmological constant there, then according to Wurtz-Noel theorem, the universe will finally evolve to the de Sitter solution. And since we know the de Sitter solution has no anisotropy, so the final solution is isotropic. But we need to put the cosmological constant by hand. So we are not very satisfied with this method. And our work focuses on the so-called MLQC1 model. In this model, we find that the shield will dynamically suppress after the quantum bounce. And this phenomenon is totally due to the purely quantum geometrical effects. It will evolve like this. Here, the exponential A is a constant. It only depends on the minimal error gap and the Barbier-Limits parameter. So this is a purely quantum mechanical result. It does not depend on any detail of the matter or any detail of the initial condition. So in this sense, we say this effect is universal. It is independent of the matter content once the weak energy condition is satisfied. Here, omega is the coefficient in the state P equals omega rho. Rho equals omega P. Here, once it satisfies the weak energy condition, then we get the result. And this mechanism is intrinsic. It is built-in mechanism. There is no fine-tuning. We do not need fine-tuning of the scalar potential or any other scalar fields. And this is unique. It is not shared by any other bounce models. And also it is robust. We check different initial conditions and it works for generic initial conditions. This is our main part of the work. Okay, so I will briefly go over the loop quantum gravity part. We will start from the Einstein-Hilbert action, the statistical variables, and finally the holonomy and flux. Okay, so to quantize the general relativity, we need to decompose the spacetime in the 3+1 formalism. This is the so-called NM decomposition. And the metric is decomposed like that. Here, n is the Laplace function, with QAB the spatial metric, and NA is the shift vector. This is the 3+1 decomposition. Sorry. Okay, maybe I need to also change the slides. Just a second.
The device. Okay, good.
Sorry for being interrupted. Okay, now here we see this is the ADM decomposition, and the metric is decomposed like that. And if we use the 3+1 formalism, the Einstein-Hilbert action can be written in terms of the three-dimensional quantities, the three-dimensional Ricci scalars, the extrinsic curvature of the hypersurface, and the trace of the extrinsic curvature. And finally, we can also get the gravitational Hamiltonian. It composed two parts. One is the Laplace function times the Hamiltonian constraint, and the shift vector contracted with the diffeomorphism constraint. And where are these constraints come from? And we can see in the Lagrangian, it does not depend on the time derivative of the Laplace function and the time derivative of the shift vector. So these two guys should be zero. This conjugate momentum of them should be zero. This is the primary constraints. And for the secondary constraint, these two momentum, the Poisson brackets with the Hamiltonian should also vanish on shell. These are the diffeomorphism constraint and the Hamiltonian constraint. And finally, Hamiltonian constraint, Hamiltonian consists of these two parts, and it vanishes on shell. So in this sense, we call the general relativity and constraint theory. Okay, this is not the whole story. We need to introduce the so-called densitized channels. Here, Q is the determinant of the QAB. And once we introduce the densitized channels, we have the covariant derivative with the spin connection. And Einstein introduced the famous variable, the Einstein connection. It is the spin connection plus gamma times the K. Here, gamma is the Barbier image parameter, and K is the extrinsic curvature written in terms of the channels. Here, A and E have simple Poisson brackets like this. Okay, and what's more, inspired by the gauge theory, Einstein write the general relativity in terms of like the gauge theory. Here, A is the gauge fields, and its field strength is the curvature here. So finally, we can use this as the basic variables.
Wen-Cong. So here just add a comment.
Okay.
Yeah. Usually the original proposal by Asteger is that the gamma equal to I.
Oh yes.
And that is a complex formalism.
Yes.
Yeah. Then later Barber changed it to 1, and the image say it could be somehow arbitrary real number. So in some sense, in this case, the most suitable name of this connection should be Asteger-Barber connection.
Okay.
Right? Because it becomes the real is very important for group quantum.
Okay. Thanks, Professor to introduce this part for me. Thanks. Okay, and this is our these are local variables. But to quantize the theory, we need gauge invariant variables. So inspired by the Wilson loop, then we will need to introduce the holonomy. But before that, we have additional constraint about the Gauss constraint because we introduced the Childs variable. So we have Gauss constraint, and finally we have 3 different types of constraint: Gauss one, the diffeomorphism one, and the Hamiltonian one. We need to solve all these constraints to get a solution. And the Hamiltonian constraint consists 2 parts: the Euclidean part and the Lorentzian part. And finally, we will see different treatment of these 2 parts. We will get different solutions and different models. This is the key part of the story. And finally, we need the gauge invariant variable about the holonomy. Here, this P is the path-ordered symbol, and E is the length along which we integrate the Asteger connection. And finally, if E forms a loop, this is the loop in the loop quantum gravity, we get an gauge invariant variable. And also here, A is in terms of the SU2 generator. So here E is an SU2 element. Okay, and its conjugate momentum is the flux. Here flux is the flux of the densitized shells. And these 2 guys have simple boson brackets. I did not put it here. And finally, to quantize the whole story, we need the wave function. This wave function is function of the holonomy. And the inner product can be defined in terms of the integration on the SU2 group. And finally, we have the wave function, we have the inner product, we have the kinematic Hilbert space. And after imposing the Gauss constraint, the diffeomorphism constraint, and the Hamiltonian constraint, we finally obtain the physical Hilbert space. This is the whole story.
I also another
okay.
comment. So here has not been finished. It's just people agree that we get the diffeomorphism in the Hilbert space. But how to imply this Hamiltonian constraint is still an open issue.
Okay, thank you. Okay, yeah, since the Hamiltonian constraint is very compact, so we need some symmetry reduced to solve the problem, right? Okay, so finally we got to the loop quantum cosmology. We need to use the symmetry of the cosmological model to reduce the story and to solve the Hamiltonian constraint. And before that, we need briefly introduce the Bianchi-1 spacetime and then go to the polymerization and quantum bumps. Okay, this is the Bianchi-1 spacetime. It is the most simplified model describing the entropy of the universe. Here, A1, A2, A3 are the different scale factors along 3 spatial directions. And we can see these 3 guys are only depend on time t. It does not depend on x, y, z. So in this sense, it is homogeneous. And the spatial part is flat. So this is a symmetry model. And we use this symmetry to reduce the Asteger variables like this. Now Asteger variable only depends on c, and the conjugate momentum depends on p. And now these 2 guys satisfy this canonical boson brackets. And also the metric can be written in terms of the variable p. Okay, so in this sense, we have simplified model using the symmetry. And
pardon? Can I go back? Yes. Yeah. If you get this, how to get this symplectic structure? Ci and the Pc.
This part.
Yes.
Okay, let me see. I think just from the very start of these two guys, right? Since we have boson brackets of A and E, and just plug this Fi to the. Okay, let's go back to. Okay, this part. So we plug the expression of A and E into this, so we can get the similar expression of the boson brackets between C and P.
But then in that case, you will find this delta function, this Dirac delta function, how to deal with that.
Oh, I see. Okay, I see. Here we.
So here, the point is like that Dirac delta function. So that means like you can actually write the symplectic form in terms of this A and E, and then there is this Dirac delta function there. That means like there is this three-dimensional integration in the symplectic form, and then you just need to substitute this expression, and you will get the symplectic form in terms of dp and dc, and finally get.
Well, in usual case, we need to derive this simplex structure from the action.
Mm-hmm.
From the action, you have this field theory, and you usually need to do some integration over a fiducial cell
Yes.
in order to get a finite result of this integration.
Yes.
In that case, usually will give a volume. The integration will contribute according to the volume of the fiducial cell.
Yes.
So in that sense, if you don't divide it by some volume in the definition of Pi or Ci, then this portion bracket will contain some volume terms.
Okay, I see.
Yeah, that is why in the homogeneous case there are some volume. Right?
Yes,
In,
yes, that's right.
in this Bianchi model, I suppose there still has this volume.
Yes, I think so. There may be some volume like this. Is the
Right.
Yes, it's the product of
Is the volume of the fiducial metric.
Yes,
is
yes,
the
that's
fiducial metric
well,
measure of the volume.
yes, that's right. And yes, there should be some volume here. I missed this part. There may be somewhere it get rid of it or maybe cancelled. I'm not quite sure. I will check it later maybe.
Okay.
Yeah, I think I agree that there should be volume here.
No,
Yes,
I mean,
because here it is.
either you define the Pi, Ci with volume, or you will contain volume in the portion bracket. I think it's the usual case.
I see. Maybe they use different
Right.
definition of psi and pi. Okay. Thank you for pointing this out. Thanks. Okay, so finally we have the simple numerical relation between these two guys, and we use this as the basic variables. So written in terms of these two basic variables, the Hamiltonian constraint, the classical Hamiltonian constraint can be written in terms of this one. We have the gravitational part plus the matter part, and it should vanish on Shear. And since we have the Hamiltonian, we can write down the equation of motion of the Hamiltonian. And this equation of motion can be rewritten in terms of the using the directional Hubble parameter, and this is the familiar Friedmann equation in the anisotropic cosmology. And for the mean Hubble parameter, we can write down the Friedmann equation, and we see there is an additional part just right here. This part describes the anisotropic, and it evolves like the 1/8⁶. So it will behave like a stiff fluid, and it will dominate in the contracting phase. It will dominate over the matter and the radiation. So we need to consider this part if we treat the anisotropic clearly. Okay.
So this sigma should be defined in terms of the rho and p, right?
Yes. Actually, it defined here. Okay. I will introduce this. This here we need to describe the entropy. So we need the Shear scalar, here we first use the unit vector of the time-length geodesic and write down the usual expansion rate like this. Here theta is the expansion. And also we can define the Shear scalar in terms of the Shear tensor. Okay, here the capital sigma square is related to the sigma squared, and it evolves like the 1 over a to the 6, 1 over a to the 6. Actually, in the classical theory, this guy is a constant. Only in the classical theory, this guy is a constant, and it evolves like this one. It will dominate in the contracting phase. So we need to treat this part seriously.
So what is this H1 do?
Oh, H1 and H2 is the Hubble parameter.
I know that, but what is the H1 do?
Oh, sorry.
This is where under
Okay.
it, they are where.
Oh,
So
okay.
where
Oh, here,
HIJ.
Here,
Ah,
HIJ
is
is
that-
HI minus HJ. Yeah, sorry, it's too little maybe. Okay. So
Sorry. So what is the rest? U, small u. Who's the velocity? Full velocity, right? That is a full velocity. To define the expansion rate,
Yes.
you have a u. Yeah, it's forward.
it's the unit vector of the time-like geodesic.
Time like
Geodesic.
geodesics.
Yes.
So is the and is homogeneous observer.
Yes, maybe co-moving observer.
Yeah, co-moving observer. I mean, because you observe the homogeneous, right?
Yes.
The homogeneous is respect to some reference.
Yes.
And
Yes.
the observers of that reference is
Yes.
forward velocity.
Yes.
Okay.
Yes.
Also have a line question. I don't know, but since the equation is cyclical symmetric with respect to 1, 2, 3, then why there is no H1 dot in
H1?
Bradman mission?
Here, right?
Yeah. When
Oh,
there is no-
six. Okay, yeah. Okay, this part. Did I miss that?
I guess it will be.
Okay, thanks for pointing out. I will check later. Maybe for the symmetry, there should be H1 dot, right?
Yeah.
Okay. Maybe I need there's typo maybe. Okay,
Yeah.
I can check later. Thanks. Okay, so we use the expansion and the shear, and especially we use the shear scalar to describe the energy.
So this U, it is proportional to particle T, right?
Yes, I think so. Or normalized particle.
Yeah.
The homogeneous observer. Yes. Yeah, the normalized one. Okay, so yeah, this is the classical story. And so for the quantum part, here we see the standard accuracy, not the modified one. The Hamiltonian composed two parts, the Euclidean part and the Lorentzian part. And here the external variable composes these two guys, and FAB can be written like this. So if we impose the symmetry, the homogeneous and the flat, so for the homogeneous, okay, so for the flat, gamma should vanish, right? Gamma should vanish, and then A and K are proportional to each other. And for the homogeneous one, we can use some gauge to make this vanish, because the derivative should vanish for the homogeneous case in some gauge. Okay, so FAB can be written in terms of these two guys. So in this sense, these guys and this guy are proportional to each other, and the HL and the HE are proportional to each other. So in this sense, we can only deal with the Euclidean part, and this is the standard accuracy. And finally, by rewriting the FAB in terms of the holonomy, and we can get the final story. Here, the holonomy depends on mu I. Mu I is the edge length of the holonomy group, right? So this guy characterizes the quantum corrections. Okay, so finally, we can get the effective Hamiltonian. It can be written in terms like this. here there are additional quantum corrections characterized by mu bar 1, mu bar 2, and mu bar 3. And they depends on the, oh, here we go. They depends on the minimum error gap and some phase space variables. Okay, so compared with the classical Hamiltonian, the effective one can be get by the so-called polymerization in LQC. It just replace Ci by the sign part, the sign mu bar Ci, mu bar I, Ci over mu bar I. Okay, this is the polymerization, and in this sense, since we have the minimal error gap, then there is a upper bound of the density. This is what we call in LQC the quantum bounds. The Big Bang similarity is replaced by the quantum bounds at the Planck density. Okay, this is the story of the standard LQC. But what is the story in the modified LQC? Okay, here we will discuss the different treatment of the Klein part and the Lorentzian part, and discuss the symmetry bounds and the theta phase after the bounds. Okay, so since E and L are actually they are different, so before imposing the symmetry, we should choose these two. We should treat these two guys differently. As I know, the earliest reference about to treat these two guys differently is written by Professor Ma and Professor Yang and Professor Ding in 2009, and they treat these two guys differently using the so-called using the so-called Timmons identity. 10 years later, similar treatment was introduced to the Bianchi model, the BI reference to the Bianchi model, and here they use the Timmons identity directly. Here, K can be written in terms of the boson brackets between A and the boson brackets between HE and V. And here they use a simple trick. First, the part of the Euclidean Hamiltonian has been regularized in the usual sense, as it has been regularized or polymerized in the usual sense in the standard LQC. And then they calculate the boson brackets between these two guys to get the result, and finally plug it back to the expression to get K. Okay, this is what their method in this paper. So this is a simple trick. Okay, and finally they get different description of the Lorentzian part. Since we have K, now we have different HL. And after this treatment, there is additional part. Yes, there is an additional part here in the Hamiltonian constraint. This part is very important since, as we can see, the standard LQC, there is no this part, right? There are only sign part. So this is the gravitational part of the Hamiltonian, and in the total Hamiltonian should plus the matter part. So in this sense, if we consider, for example, if we consider large volume, since we expect after the bounce or far away after the bounce or far away past the bounce, there should be classical phase, and the volume should be large, and the matter part can be ignored. So then the gravitational part should dominate. Now, H should vanish on shell, right? So if there is no this part, when H vanishes on shell, these two guys should vanish. So when these two guys vanishes, it reduces to the classical story. So let's go back to the process of the polymerization. Okay, we can see these two guys. These two guys. So the effective Hamiltonian can be reduced to the classical Hamiltonian when this guy is much less than 1. So when this guy approaches to 0, the effective Hamiltonian will reduce to the classical Hamiltonian. Okay, so in the standard LQC, let's go back. Okay, sorry. Okay, so in the standard LQC, if there is no this part, then for this part, when H vanishes, then these two guys should vanishes, and finally it will reduce to the classical phase. Okay, this is the story of the standard LQC. But for the modified one, there is additional part, this part. So when H vanishes, then there is additional solution, asymptotic solution described by the vanish of this part. Okay, later we will see it is just this additional part which corresponding to the de Sitter solution after the bounce. Okay, this is the key part of the story. And in this sense, we have a symmetric bounce. Before the bounce, there may be a classical phase, and after the bounce, there are the de Sitter phase. These two phases are different, so we call the bounce asymmetric. This is the key ingredient of the story, which later will produce us the K of the Shear. Okay, so this is the reason why there is emergent the Sitter-like phase after the bounce, because this part can be zero, not this part. And our work is to find out the shear damping mechanism just due to the emergent the Sitter-like case, the Sitter-like phase. Okay, so let's go to the mechanism of the quantum damping. Okay, here for simplicity, we treat the entropy as the perturbation around the FLW model. So we treat the entropy small. So we just write the scale factors like this. Here, theta are small parameters, and also pi can be written in terms of that. And Ci also have a small fraction around the FLRW model. Okay, so for the isotropic part, we can write down the equation of motion of this part. Okay, this is the equation of motion of the modified LQC1. Okay, we can see there are two parts. Here, B is the volume, and B is defined by C over A. Okay, these two guys compose the two basic variables. And here, B depends on the P. P is the pressure, of the metal part. So when V is very large, we can ignore this part. And these two guys can be solved asymptotically. Here we have the F and G. They appear here. Later we will use them.
So what is B here?
B, this one.
But what is C?
Okay, C is the
C is the back. Is somehow like the
yeah,
background.
yes, the FLRW part. It is the mean part. Okay, so finally, we can solve the isotropic part first. Okay, so we can solve the isotropic part first. We have these three independent asymptotic solutions. We can see there are 0, the plus 1, and then the minus 1. For B equals 0, we have the derivative of B and derivative of V equals 0. This is exactly what appears in standard LQC. This is the asymptotically classical phase. Okay, this is the asymptotically classical phase. But there are additional asymptotic solution. This solution is totally due to the cosine term in the Hamiltonian. This part is totally due to the cosine part in the Hamiltonian. And we have these two additional asymptotic solutions, which correspond to the de Sitter contracting and the de Sitter inflation. Okay, so we choose the de Sitter inflation after the bounce. It is the de Sitter evolution like this. Especially the exponent only depends on delta and gamma. Here, delta is the minimum error gap and gamma is the Barbero image parameter. So this is totally due to the quantum geometry effects. It does not depend on any detail of the matter. This is the key ingredient of our story.
So this should be the same as the result given in this MLQC, right?
Oh, what C?
I mean, this result
Yes.
should be the same as that given in this MLQC model.
Yes, this only appears in MLQC1 model.
Okay.
This only appears in MLQC1 model, since this part, these asymptotic solution.
No. So my point is like here, so you consider this anisotropic model and then you do the perturbation. And there is this isotropic background.
Yes.
I mean, this isotropic background should be the same as that given in this isotropic LQC.
Sure. Okay, so this part is the isotropic part in the MLQC1. Actually, this part have been analyzed about in maybe in 2018 or later. Yeah, this part have been analyzed far ago the Bianchi one. Okay, so this part is also the equation of motion in MLQC1, but it is the equation of motion in the FLRW model. Okay, so we treat the anisotropy as the perturbation around this model. So in this sense, we simplify the calculation. Okay, so okay, this is the asymptotic solution of the isotropic part, and for the anisotropy, we can write down, or we can also write down the master equation of the anisotropy part, and we can see this curvature F can be totally written in terms of F and G. Okay, and also we find simple asymptotic behavior of this damping function. It behaves like this. It behaves like this. Okay, now we finally come to the key point for omega greater than -1. For omega greater than -1, here we see, and then Ft will approach to some constant, and this constant only depends on delta and gamma. It is merely it's a totally quantum geometry effect. Okay, in this sense, F approaches to some constant, and plug this back to this equation, we find the general solution of sigma I. Okay, and the constant part can be absorbed by rescaling of the coordinates, and we find the theta decreases, the anisotropy part decreases exponentially. This is the key part of our work. And here, yeah.
So can you remind me what is theta?
Okay. Okay, here theta is here. It describes the perturbation or anisotropy around the FLRW model.
I see.
Okay. We treat this part as the perturbations. Actually, we can go beyond the perturbation proof, but here for simplicity, we just write down the perturbation
And
model.
then how do you get the equation of the next slide?
This one?
No, the master equation.
This one?
Yeah, how do you get
Oh.
this master equation?
Okay. So you see here,
Uh-huh.
the second one and the second one, we can just get rid of this part and just do the second time derivative of the sigma I, and finally get rid of this whole part, we can get it.
Yeah, but the point is like if you do that, there will be also this delta C dot, right?
Yes, so we have delta C dot, right?
And then there will be this delta C in your equation for the second order derivative.
They can be cancelled. Actually, when you try to calculate it, it can be cancelled. Yes, we can get rid of delta C and just write down the second derivative of sigma. Why we try to write down the second derivative is just to want to get rid of it.
Okay. So you mean it is cancelled when you do calculation? Or you just omit it by hand?
No, not omitted by hand. It can be cancelled. Yes.
So the I is only the spatial.
Directions 1, 2, 3, x, y, z. 3 spatial directions. Okay, so okay, finally we have the master equations. We have simple asymptotic behavior of the curly F, and we solve this equation and find the exponential decay of the anisotropic part. Okay, this is the key ingredient. And finally, we can plug this expression back to the sigma squared. We can plug this back to the expression of the sigma squared. Just calculate the sigma squared, and we also find it's exponentially decay like this, but only the 2 times the A. Okay, so here A is also the previous constant. It only depends on delta and gamma. And now we have a purely quantum geometry effects which describe the exponentially decay of the sigma squared, the shear scalar. This is the main result of our work. So in this sense, we say this is an universal behavior. It is independent of the matter content, of course, since we only require omega greater than -1, right? And we later will show that the decay rates are same for dust radiation and scalar field, since we have analytically confirmed that A is only depends on delta and gamma. It has nothing to do with the matter part. And also it works for generically initial conditions. Okay, so the physical interpretation is that it due to the asymmetric condensation of Euclidean and Lorentzian sectors in MQC1. This is the key part. Since the asymmetric condensation gave us the cosine part in the Euclidean, in the Hamiltonian, and then we have the single solution, and finally we have the decay of the shear scalar. Okay, this is the
So,
Okay,
sorry, so why this condition omega greater than -1 matter?
Here we go. Here, yes. We need the decay of this part. We need the decay of this part. Then, if omega greater than -1, then this part will decay, and finally, curly F approaches to constant. And plug this back to, we have the exponential decay.
And another, what is omega is
The coefficient in the state function.
okay.
Okay. So, okay, here we go. So we finally have the exponential damping. This is the analytical mechanism. And finally, I will show the numerical results. Okay, so for numerical results, we can go beyond the small motivation. So here, we choose initial condition like this. P1, P2, P3 are different from each other, and this far go beyond the perturbation theory. So, so we finally find the results. The bouncing time is about approximately given by 26 Planck time, and the shear decay rate is given by this. This is the same. Okay, here we go. This is the same as the 2A. Okay, we numerically fit to get this part, and it fits to the analytical results perfectly. Okay, so we also compare the classical GR, the standard LQC, and the modified LQC1. Here is the main result. Here for the red one is the GR. It will diverge. The sigma square will diverge at the singularity. And for the MLQC, we can see there is a bounce. There is an upper bound of the shear scalar, but it is still there. It remains there after the bounce. Okay, so only in the modified MLQC1, it decays exponentially after the bounce. Here is the main result. Here is the main result of this work. Yes. Yes. Okay. So we finally announced that this is due to the asymmetric condensation of the Euclidean and the Lorentzian Hamiltonian. Yeah. This is the main result. Okay. We also show the evolution of the scale factor in different scenarios. In classical GR, we can see there is singularity. It stops here. And for standard LQC, yeah, in this initial condition, it behaves like this. There is an dimension which still remains in the deep compound region. Okay, in small, it is very small after the bounce. And for the MLQC1, these guys grows exponentially after the bounce. They grow exponentially, and they have the same exponent A. They have the same exponent A. A is just the one written in terms of gamma and delta. Okay, this is the different evolution of the scale factor. And we also consider different types of the matter: the dust, the radiation, the massless scalar, the abirotic potential, the polynomial Peltier potential. Okay, but we find the same decay rate, for this different matter part. So we call these guys universal. It does not depend on the matter content. Once it is satisfied the weak energy condition. Okay, yeah.
And do you
so-
have any constraint to the matter?
And this constraint, we need to consistent with the weak energy
With respect to
condition.
the energy moment, energy condition.
Yes,
What kind of energy condition?
weak energy condition.
Okay.
Yes. Okay, so, but what's more, we need to say that the decay occurs in the deep quantum region, the deep quantum region. Here we go. Since this part is exponentially increased, right? Exponential increase is like the theta phase, and it generates an effective cosmological constant. It generates an effective cosmological constant due to the quantum geometry effects. So this part is totally in the quantum region. This part is totally in the quantum region. Okay, so the decay occurs in the deep quantum region, and it is much before the classical limit is reached. And this is it demonstrates the quantum gravitational nature, and they have the same form of the exponent. Okay, so we show the different the radiation, massless, periodic, and chaotic mass. The matter part, and we show that they have different time for the bounce, but they have the same exponent decay. They have the same exponent decay. Okay, once the weak energy condition satisfied. Yes. We finally come to the conclusions. So, in our work, we have identified a defining feature of the MLQC1 model. It exponentially suppressed the shear immediately after the quantum bounce, and the decay of the shear scalar occurs in the deep quantum region. And these properties are universal, does not depend on the matter once the weak energy condition is satisfied. It is robust. It does not depend on the initial condition once the contracting phase is satisfied. And it is intrinsic. It is due to the building quantum geometry effects. And we see the POD A only depend on gamma and delta. The same decay rate, okay, this A only depend on the quantum geometry effects. And it is unique. It is not shared by other bounces models. So this mechanism solves the anti-shock problem in this sense in the bouncing cosmology without fine-tuning and additional assumptions. And in the future, we may try to extend the model to the Bianchi 8 or Bianchi 9, and maybe we also need to work out the detail of the classicalization. Since the bounce, we see since this part is in the deep quantum region, we do not want the inflation exist too long. We need to exit it. We need to end it. So especially we want to come to the classical phase. So later we are going to find out the mechanism to exit this part. Okay, this we call the so-called the classicalization mechanism. Okay, also we can work on the observational implication for the CMB, and we can work on the connection to the full loop quantum gravity. These are the future directions. And thanks.
Okay, any questions and comments?
Yes. Thank you for very interesting talk.
Thanks.
And very clear. Is there some observational restriction on this decay factor A?
Okay.
It has to be some value or?
Actually, we still don't know. Maybe there can be some constraint from the CMB. Yeah, but we still don't know. Maybe later we can work on the power spectrum or something like that to connect to the CMB to constrain the decay rate. Yes. Yes.
And then you said you want to extend this framework to Bianchi
Yes.
8
Yes. This
9.
part is very hard.
So I'm not quite familiar with this classification of BNC models. So why you only consider these two models?
Actually, these two parts are more complicated. They introduce some curvature correction on the anisotropic. So this part may introduce some additional effects because it is related to the curvature itself. And for the BNT1, we see it is homogeneous and flat. It is very simple. So once there is some curvatures, we don't know whether this mechanism can work.
But how about from 2 to 7?
Yeah, maybe, yeah, we can check it one by one.
But using these two are important.
Yes, because these two guys are the most
Quite different
complicated.
from the BNT1 model.
Yes.
Okay, thank you.
Thanks. Any more questions?
我有一个问题，就是你前面的那个Shear 的平方在标准 LQC 模型里那个图，对，就这个，我看它也是那个下降的那种，就是反弹以后它也是在下降的。然后
对，
它是按照你前面说那个，就是大西格玛的平方，然后乘上 a 的6次方分之1的那种变化。
那个就 sigma 平方除以 a 的6次方，那个是在经典极限下是对的，是在经典极限下是对的。但是呢，它会有一段很长的，就是这个量子区域，它不会很快就 reduce 到经典区域，所以它会保持一段很长的这个量子区域在 standard QC 里。
就是说它也是在下降，但是下降的不够快。
对，可以这么说。
然后就是
除非它后面退化到了这个经典区域，也就是所谓的 mu bar ICI 非常小于1的时候，当满足这个条件的时候，它退化到经典区域了，那么刚才说的那个 sigma 平方除以 a 6次方这个公式才能用。
就是说你期望这个东西可能如果不下降那么快的话，会明显违反这个 CMB 的观测，是吗？
对，我们现在还不确定，主要就是它确实会一个是保持比较长的一段时间在，就是在那个 post bounce， 也就是这个 post bounce 之后的初期嘛，它会保持比较长的一段时间，所以它可能会保留一些比较强的各项异性的印记，对，所以我们期望如果能够快速下降。
然后还有个问题就是，你这个快速下降可以从这个微扰，就是在这个各项同性的基础上做各项异性的微扰，然后推出这个微扰是指数下降的。那如果在标准 LQC 里也做这个微扰，是不是就推不出来这种指数下降的？
推不出来的，因为它指数下降是非常依赖刚才说的，非常依赖于这个解，它要有这个解才行，有这个 de Sitter evolution 才行。这个解的存在呢是 B 要取这个分支，取这个严格来说是取 B 等于负的这个分支，对应 V 的导数是正的这个分支才行，它才是一个德希特膨胀的这样的一个 inflation 的这么一个解。而对于 standard QC 的话，它只有这一支，这就是刚才所说的，因为它的哈密顿量，在 standard QC 里面只有正与前面的这个意象。那么 h 等于0的时候，那只有 sin 这个等于0，那你就会发现它就对应的就是 b 等于0的那一支，而只有后面这一支为0的话呢，它对应的是 b 等于非0的正负的那一支。所以这一项的存在是非常重要的，而这一项的存在就来自于欧式项和这个罗伦兹项它们的不同的处理。
再翻回去刚才那个方程看一眼。
哪里？
就这个。
OK。
它这个 v dot 然后等于正比于一个 v， 所以能解出 v 是以指数的形式。
对。
然后那上面那个 v dot 等于0，说明 v 是不变的，是吗？
对，它就是一个 classical phase， 这样对应的就是，我们说是 classical phase， 严格来说就是类似于这样，会保持比较长一段时间的那种就渐进的指数。
然后还有一个问题就是说，你说这个下降是发生在这个 deep quantum range 这个。
对，就是这个地方，它对应于这个德希特暴涨，而德希特暴涨其实就是刚才解出来的 b 等于正负的那一支，对不对？它完全是依赖于就是所谓的就是量子几何效应，就是这个完全依赖于这个 A 的，而且在这个区域期间，呢，就是 mu bar ICI 呢，它是不等于1的，不等于0的，它不等于0的， 所以它会远远的，就是跟零离得很远，所以我们把这个区间呢称作是 quantum regime。
就是这个区间它的要求是什么？就是那个 mu bar ci 要大于1吗？还是？
不是，它算出来的话，它基本是，我有点忘了，就是它不等于零，它离零很远，具体是多少有点不太记得。
就这个 mu bar I 乘 ci 要大于0，就是那个。
不是，不仅仅是大于零，而且要离零比较远，可能要接近，因为它是 sin 嘛，sin mu bar ICI，对吧？sin mu bar ICI，所以 mu bar ICI 呢，可能要接近是2/派1.5几可能要。
哦。
对。
好，谢谢。
不客气。Any more questions？
说明有两个，第一个是来源的问题，就是你刚才说那个，你这非常依赖于对于一个欧式的和一个那个
洛恩兹的
这样一个不同的量子化，对吧？
对。
然后那个我看哈密多量，我不知道为什么一个叫欧式，一个叫洛恩兹的这个解释。
这个，我印象中就是如果你是整个一个欧式的这个作用量的话，你最后得到的就只有正比于这个Euclidean的这一部分，就不会有后面这一部分，所以把这前面叫做欧式的。
你所谓欧式就是我所有的 selection 都是正，是吗？
对。
然后你要如果说有那个负的话，就出现那个 ACL，是吧？
对。
所以这两个我没有理解，那这两个哈密多量同时都有是吗？
对啊，如果你后场是负正正正的话，那这两个都是有的，它是一整个哈密多量里面的两个部分。
OK。它是
就是它如果要是欧式引力的话，就只有这一项；但是如果要是洛伦兹引力的话，就是两项相加，所以它管这个叫欧式，叫洛伦兹。
你说欧式，比如说我就是一个纯粹的，
就是
三维引力，
就是一个4维度规那个
全是正的那种，就只有第一项。
对。
如果有负的话，就两项都有。
对。
OK。那我还有第二个问题，第二个问题就是那个你那个24页。
24页。
对，好像是24页吧。对。
这个。
那个上，对，是那个有一个就 matter 的那个，是22吗还是25啊？
这个。
对，这一页里面为什么这个 massless 的和那个所谓 chaotic 的，它们是一样的？
这个我们没有仔细分析，不过本质上它们毕竟都是标量式嘛，标量式，它可能这个不是很影响它。对。我们也觉得有点奇怪，为什么他们两个重合呢？anyway， 不过这一部分没有仔细分析就是。
反正我不知道你 chaotic 什么意思，其他的我也知道。
OK， 它是一个多项式的，一个式。它是一个多项式的，就是1/m方后面再加上一些可能4次方啊这样的多项式，有点像刚才他们讲的标量的这个。
所以你 massless 就是 v 等于
0。无质量的，对，就是 m 等于0嘛，那后面也没有其他的那些东西。
对，所以你 massless 跟 chaotic 都是标量场还是？
对，都是标量场。其实这个所谓的 equilibrium 它也是标量场，它只不过它是一个很奇怪的一个特殊的式，要取那样一个特定的形式，他们之前才讨论的关于那个一些其他的一些东西。
所以你说那个有反推动是这个意思？
对，可能是对式的某种特殊的选取。但我印象中，我其实对这一块也不是特别熟悉，但我印象中是他们选取这个式，一个是为了解释这个各项异性问题，但是他们会存在一个问题，好像是在某些数理条件下，这么选的话，它暴涨就消失了。好像在某些数理条件下，他们暴涨就没有了。但这也是这个式可能有一点点问题的地方。但我不确定了，这块我确实不是特别的那个关注。我们只是选取了这几个不同的物质场部分来做这个数值的计算。
就那个 chaotic 那个 potential 其实是因为它是最简单的一个多项式 potential，然后那个暴涨消失其实跟那个 initial condition 选择有关的。
OK，thanks。
So I actually have one question. So you can go to.
Okay.
So the point is like dumpling of the shear exactly means like this. Oh yes, this page. Yeah. So the point is like that means like it is used to. Yeah, it is used to measure the difference of this tree three skew factors.
Yes, the relative difference.
Yeah, the relative difference.
Yes, I think you see these three guys are still different, right?
Yes, yes, yes.
Yes, but the relative difference should vanishes.
And then that means like okay, so the relative difference between them just because it is exponentially you mean okay so okay so
Yes.
the point is like the relative difference of these three, so it's like exponentially decay. So that because like the a for each a they just like exponentially expand.
Yes.
Is that the reason?
Yes, yes, because just due to the exponentially expand of the scale factor.
And then I say so if I have some cosmological model, so where those a's just exponentially increase, and then the share of this will be just exponentially.
Maybe we but we still need to calculate and check. But maybe if there is additional model in for the inflation part, maybe the
So what do you mean by relatively
just
relative
exponential
difference?
relative difference.
Like a1 divided by a2?
Yes, a1 minus a2 divided by a2 over 1, like this.
Yeah, so I think the point is like for instance if you have like two numbers which are exponentially increases with
Yes,
respect to
yes,
t.
yes.
One is like exponential t and the other is exponential of 2t. And then you use this exponential minus the other exponential divided by this exponentials. It could be like exponentially.
Yeah, maybe.
Yeah.
Yeah, maybe. But the evolution is totally due to the MLQC one.
Yeah, I know, yeah, okay. Okay. Okay, so if there is no other questions, so let us thank our speakers today.